Hello.
So,
Hey. So, mm, yeah, I forgot to tell you guys that today there is a class, but I thought that it was kind of understood. So hopefully, there's no miscommunication as such. So, so yeah. So tell me. So, do you have any questions, doubts regarding this stuff that was done? This Max-Lumin theorem on network flows in general. I saw someone has asked me to explain this Hall's marriage theorem and how does it come out from the maximum theorem. So we can have a look at that. But other than that, any other questions?
regarding the assignment,
Yeah.
uh, for the polygon question, like we have to find a triangulation.
I think I'm not taking a look at that. Shit. Just one second. Regarding the
I think it's question 3.
question three, right?
So we have P points and we want to find the minimum cost triangulation.
Right. Right.
Uh, can we assume is there some sort of order in which the points are, or are they given randomly? It's question 4.
What the question? So you can think of it giving randomly. I mean, there's no particular order in which it has been given as such. But if you want to sort it out in some particular way, you can do that also. Right? You can
I
sort it
mean,
in terms of.
I'm not really sure how to sort a two-dimensional set of points.
You have to sort it in terms of either x coordinate or y coordinate, or maybe distance from the origin or something.
Like what I wanted was if I and I plus 1 are two adjacent points in the given list, then the edge joining them should be edge of the polygon, should not be a diagonal. The line joining pi and pi plus 1,
Yeah.
that should be a edge, not a diagonal of the polygon.
Right.
So basically given in clockwise or anti-clockwise order.
Okay, let's start with that. Let's have it that you can have it been given. Okay, in a clockwise or anti-clockwise order, and let's see after that what happens. Okay.
Yeah.
So I assume that is given in a clockwise and anti-clockwise order, and then solve it, and then let's see whether we can remove that condition somewhere later on.
Sir,
Yeah.
sir, in question 1 of the assignment, we can generate in, suppose n is 20, then we can generate suppose 5 plus 5 plus 10 and also 10 plus 5 plus 5. Should we consider these two as different or the same? I mean, will you count it as 1 or 2?
We'll count it as 2.
Okay, sir.
We only want a Boolean in question 1, right? We don't want the number of partitions.
No, we don't want the number of partitions, but I mean, count the number of ways we can generate, right? So yeah, we given a number n, and it's like count the number of ways you can generate n with the coins of s. So the coins are, say you have coins 5, 5, and 10. And how many ways can you produce 10? Okay, so maybe since people have asked me this one, let's talk about it now. No, let's switch later. So why did you ask me? Why did you ask me the Boolean thing? Let me.
I got confused with question 3. I was thinking about question 3.
Okay, okay.
Question 3, we have to return if we can find the 3 partition or not.
Okay, okay. Okay. Yeah, the reason I was asking you because I mean we will very shortly make a distinction between, I mean, or have a connection between the optimization question and the Boolean question. So yeah, we will do that maybe next week. So I thought that you were kind of hinting at that thing.
Sir,
Yeah.
in the book,
Mm.
in page 350, there it is given that given a flow f of maximum value, we can compute an SD card of minimum capacity of order m time. And here they use the breadth first BFS, breadth first search, and uh, order, but breadth first search takes order of m plus n.
Yeah, the m plus n and m is kind of same, right? I mean, like, yeah, it is kind of, I assume that, yeah, I mean, you can think of that m is greater than n. Because if m is less than n, right, what does it mean? What does it mean m is greater than n? First of all, when you start from a particular vertex, right, you will not be able to, you will only be touching only those set of edges that are in the connected component, right? And in the number of edges in the connected component must be more than n minus 1.
Yes, sir. Yes, I got it.
So, I mean, yeah, so this is like, yeah, order m plus n is same as the 3 order n. Yeah, in the actual breadth first search, yeah, go ahead.
No, so it's not related to this. Yes, can you post the assignment as an assignment in classroom so
Yeah,
that we
I'll
can?
do that. I'll do that. Okay, so actually the assignment has been is given, right, and the due date will be sometime next week. But in the meantime, what we will do is that this is something very important that we will do. Okay, so I will do certain things today. Okay, I will do some slightly different stuff than what was done till now, and I will we will try to give you a collection of questions. Okay, and I will tell you what are the questions soon, and you are expected to kind of solve it and come to class next class or Tuesday or something with those things tried out. Okay, so you don't have to submit them, but those are the things that I would really need you to guys go over once. So this is a deadline of this particular assignment. The assignment 5 is maybe Tuesday, the next Tuesday, right? But also yeah, so the next Tuesday, and but this question that I will give you today, you have to do it by, so sorry, not next Tuesday, but when. So let me just open this deadline stuff. Just one second. Yeah, so today is 5th, right? So the assignment due date will be on the 15th. Okay, the assignment will due on the 15th, so you have more than a week. But I will be giving you a set of questions that it's pretty easy, but it will be very important for you guys to go over it. And that will be, you have to do it before Tuesday 8th and come to the class. Okay, so you can, if you want, you can push the assignment by some more days. Fine? And yeah. So maybe, so suppose that you guys have a class at 1 o'clock today, so I need to jump straight into whatever we are doing today. So any more questions about the network flows and all? No? Okay, if not, so I know that there is one question that has been asked about the matching. Okay, so I kind of had a vague statement that was told last time. Oh, I've not shared my screen. Yeah, can you see my screen now?
Yes, sir.
Yeah. So you had this. We had done this max flow min cut theorem, right? And so basically, it kind of told that given a network flow, the maximum flow is equal to the minimum cut. But I also told something about the matching. You remember this matching, the definition of matching? So let's think of it a bipartite matching to start with, okay? So meaning the graph is a bipartite graph. You have A and B, and there are edges between A and B. That's it, right? Some kind of stuff like that. And question is that can you find a match? Okay. Now, okay. So what is the matching? How many of you tried to look up in the internet of? So the question was about something called a Hall's marriage theorem. How many of you have even looked at it? I want to know.
Sir, I looked at it.
Yeah, you have asked me this question, so you must have looked at it. Who else?
I did as well, but like I completely forgot the proof of Hilbert's theorem, so this proof wasn't very clear.
Sorry.
I forgot the proof of Dilbert's theorem. Like
No.
the proof
Yeah,
for this is Dilbert's, right?
No. The proof of this one doesn't require anything. You can follow from maximum infer.
Oh, the proof I saw used Dilbert.
Yeah. So there is a lot of proofs out there, but there's one proof that follows directly from maximum infer. So maximum infer is a bigger hammer, much bigger hammer than maximum. What about rest of you?
Sir, I looked at the wiki page.
Yeah. You look at the wiki page. So you have seen what the statement is.
Yes.
Okay. Or what? Yeah.
So I went over the definitions of the matching or some sites.
You went over the definition of the matching, but did you manage to read the statement of the Houseman theorem?
I actually read it quite a while ago in the book itself.
Okay, in the book itself. Okay, fine.
I know the statement. I saw it, but
You don't know the proof. You could not
no,
get the proof.
no.
Okay, fine.
Sir, I looked at the wiki page.
Yeah, but okay, Wikipedia is perfectly fine. But you looked at the proof or the statement, or did you understand the proof, or what is this scatter?
Sir, I tried to prove it by myself. I haven't yet looked at the proof, so I was.
Okay, fine. Okay.
Sir, I looked at the statement and I was reading further, but there is a concept of Hall violator I could not understand.
Okay, you don't need any of those things. Believe me. I mean, his statement and max flow min cut will give you the Houseman theorem.
Okay, sir.
Okay, but yeah, I will give you some hint of it. I will not give the full proof of it. Okay. Anything else? Anybody else? I have got to know from 7 people till now, and there are 15 people. What did the rest 8 of you do? I mean, I can start asking by names. I mean, is this all that we have come down to? Prasunte?
Yes, sir. I told you that I looked at the wiki
Okay, you
page.
looked at. Perfect. Okay. Akraprabha Sanki?
Sir, I told that I saw it,
Okay,
but I
you
don't
saw it.
have-
Okay. Then Tarusri?
Sir, I looked at the Wikipedia page.
And you saw what? I mean, you did look at the statement of it or proof of it or what?
Only the statement.
Only the statement, okay. Kirti Agarwal?
Sir, I did not look at it.
You did not look at it. Okay. Saswata Naha?
Sir, I tried to understand the proof, but not till now, not completely understand.
Okay, but you have
But
tried
still,
to
I
look
know the
through.
statement.
You know this statement.
Yeah.
Okay. Then where is it there? Let's see. Adam Tayabji. Are you there? Okay. Okay, I got some idea. So Nirmal Mandal. Okay.
Yes, sir.
You took, did you read it?
Yeah, I have seen from Wikipedia page, but not totally understand.
Okay. Okay, fine. So good. So I think that many of you have taken a look at the Wikipedia page and this has written the statement of it. Okay, so that's more than perfect for me. Okay, that is like you had a good start. Okay, so let me just tell you what is the statement. Okay, the statement is kind of clear, but simple rather. But before I go into statement, I have to define this concept of what is called as a perfect matching. Right? What is a perfect matching? A perfect matching is one in which every vertex in A is matched to every vertex in B. In some vertex in B. Okay? And let's say that, so to make our life slightly simple, let us assume that size of A equals to size of B. And the perfect matching is that for all X in A, there exists a Y in B such that XY is in the matching M. Now, of course, the idea is that if XY is in the matching M, then if there's some other X prime, then the Y prime will be somewhere else, right? You cannot have in the matching, no two vertices can come in common, right? So it is the reason it is called matching is you are trying to match between, you have to produce a match between the set A and set B, right? And so you want to do a one-to-one mapping between the set A and set B. Now, let's try to see when can we say that there cannot be a matching, okay? So, say here I have 4 coins, four elements, and I have this kind of stuff. Does this one have the matching? Does this graph have the perfect matching?
Not possible.
Why?
The first 3 vertices in set A only accept 2 vertices in set B.
Right. So basic thing is that answer is of course no. And why? Because if there exists a subset, okay, say U, which is a subset of A, right? Such that like look at the neighbor of U. So U is a subset, okay, not a vertex. It's a subset. Neighbor of U. What is the neighbor of U? Of course, neighbor of U is a subset of B, right? And if size of U is strictly bigger than the neighbor of B, neighbor of U, sorry, then what is it? That say maybe 20 people is asking for 19 things. Then can you satisfy 20 people? Of course not, right? So here there are 20 people asking for 19 things. The neighbor of U is strictly less than U. So if this statement holds, then there doesn't exist a perfect match. Okay, so this is one part of the statement of the Hall's marriage theorem. Easier part. Okay, Now, Hall's marriage theorem is actually the if and only version of this. So what does Hall's marriage theorem say? Now, I mean, I don't have to explain you why it is called a Hall's marriage and this whole thing of matching and everything going on. You understand what is the context in which it was defined. So if you like this kind of this part of work, it's called a matching theory. It's a very big matching theory concept. There's a subject here, and there are a lot more interesting results that are still needed. And I can tell you a lot of interesting stories. So there is something called a little bit more complicated thing called stable matching theorem. I don't remember whether I had spoken about this stable matching theorem or stable matching as such anytime in this class or not. Okay, if you look at the Kleinberg-Turtle's book, the Kleinberg-Turtle's book starts with stable matching. The first chapter deals with stable matching. Okay, and it's a very beautiful concept, and it's kind of try to model theoretically when can you call a marriage stable, and how do you produce a stable marriage? Of course, it is all in the language of matching theory. So it's the language of graphs and algorithms and all. And you might think that this is a very funny subject to look at, and maybe a bit shy about it in your right now about talking about this kind of stuff. But this concept of stable matching marriage theorem, if you are interested, please take a look at from the book. Kleinberg-Turtle has that. And this thing was a very interesting result. This one was the first non-trivial algorithm for this one was given by these two persons of Gale and Shapley, two economists who ended up getting Nobel Prize for this one. Okay, so it is not trivial object. It's pretty non-trivial stuff, you understand.
In which subject?
They got it in economics. They got it in economics because stable matching is basically a concept that comes from the game theory world also. Okay, I mean, a lot of things that we talk about comes close to the economics world or the biology world and so on and so forth. Okay, I mean, yeah, I didn't do a proper job of it, but you did this problem of the longest sequence, subsequence, and string matching and all those things, right? So I don't know. So something like 15 years ago or 20 years ago, one of the biggest projects of humankind that has ever been taken has been the concept of Human Genome Project. Maybe many of you are not even born at that time. But the idea was that the whole gene sequence of the human beings was kind of written up properly. Okay, what does the single gene of a gene of one person looks like? Okay, the whole gene was sequenced, and the way it was done is that the gene is a massively big enough thing. It's like the total space required to write one single gene effort is something like a few terabytes of data is required. It is stored in a single cell of our body. But so it is impossible to sequence it in one go. So what they used to do is they break it up into chunks and small parts and all those kind of stuff. And then finally they have to use lots of mathematics to pull it back together. Okay? So although, of course, there's a lot of biology, there's a lot of chemistry that goes on. But one of the main crucial aspects of this whole thing was to design algorithms which manages to do the sequencing and tying up these sequences and all very properly. It's pure computer science, pure algorithms, and like I mean, at the end of the day, it comes out to simple algorithms that ended up going into the biology world, and all the various awards and all they get it and all. It's one of the biggest stuff. So whatever you are hearing of human genetics now is thanks to this level. So similarly, there is this thing of Gale Shapley who worked on this stable matching theorem. That's a very, very there's a concept. This is a very important concept that is it's a finally algorithmic question, but this has a lot of big implications in lots of other things. Similarly, there are, John Nash's work, that is also very much mathematical and algorithmic concepts, finding equilibrium quickly and so on. So this whole subject of computer science or theoretical computer science, and in particular algorithms, has extremely strong connection to almost every field of research that you can think of, particularly nowadays. So, okay, coming back to Hall's, enough of this ER for algorithms. So, what does Hall's theorem say? Hall's theorem says that a perfect matching exists if and only if, okay, it's an if and only if statement, for all subset U of A, okay, take any subset U of A, the neighborhood of U must be bigger than the size of it. Okay. That is what that's it. That's it. Okay?
Yes.
Fine. So of course one side is obvious, the other side is the hard part. Okay. Now let's see how can you think about solving it. Now you remember that we had kind of started with Marais theorem, the matching theorem, and then we talked about flows. So how do you model matching in flows? Right? So you have this graph here, some kind of graphs over here, and how do you model things in flows? One way is to kind of join all these vertices in A with a start vertex S, directed. Yeah.
So it will be greater than equal to.
And all the end vertex here with the end vertex T. Now, idea is that you don't want to send more than one unit of flow in each of them. Okay. So you want to maximize, so you want to keep a capacity of 1 in each of the everywhere. You have to put a capacity of 8 in each of the everywhere. Now, what about these weights here? Okay, these weights here, you can either put a capacity 1, because anyways, 1 unit will go to 1 unit and that's it, right? Or if you want, you can even put a capacity infinity. Okay? Because if we push 1 unit here, then of course you cannot send more than 1 unit in any case, even if the capacity is high. So first thing to observe is that in this network, so let's call this network, okay? This network, okay? Oh, and I direct all the edges in this direction. Okay? The max flow, okay? Now when is the max flow end in this network? Or when is the max flow, so size of A? So max flow is that size of A, but anyways, the sum of them is only size of A, right? Because only size of A number of ones are going out of S. So max flow is is A, meaning you have to push 1 unit from each edge. Okay? Now this thing after coming here can split into 2 parts. I mean, 1 unit can be pushed here, then half unit goes there and half unit goes there. But again, if you recall the max flow Minter theorem, it has a very interesting statement there, and this is a very useful statement to remember. That if the capacity of every edge is an integer, then just recall how we use the Ford-Fulkerson method, right? Then the max flow must be an integer, and the flow on every edge is also an integer. Because every time you kind of find a edge in G or in G prime or something like that, that flow is incremented by an integer amount. right? So the total flow on each edge is an integer. So what does it mean? It doesn't mean that there is no flow of, there is no max flow where there is fractional flow going through a particular edge. All it says that there exists a max flow where every edge has flow integer. So this is something that, this is the observation from Ford Fulkerson. And this is a very useful observation, so remember this observation, okay? So if the capacities are all integers, then there exists a max flow. See, I have written there exists, not for all, okay? There exists a max flow with flow on each edge being integer. Okay. I am not going to say too much about it, but if you want to think about it, it should follow automatically. If you understand the proof of Ford Fulkerson or Ford Fulkerson, this theorem should come out naturally. So what does it come down here in this picture? In this picture, so that means if it is an integer, that means, so since everywhere it is integer, so 1 and infinity, all of them are integers, right? So if I push 1 unit from here, so there is the integer flow. But with this 1 unit cannot be split further. So either it will go on this edge or this edge, right? So somewhere. So it will kind of go on this edge, say, and then after coming here, it will go on this edge. Similarly, this one will come on here, then go here, and then go here. Note that it is kind of creating a matching between A and B, right? So this network has max flow A if and only if the matching, the graph AB, right, has a perfect match. Do you guys see this? Should I repeat this part? I mean, although what about rest? It is an observation. If you want to say it formally, you might want to write a few more words, making it a claim or lemma or something like that, or a theorem, right? But is the idea clear?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So when can the max? When can this AB not have an imperfect matching? Can you now use this observation and Max-Flow-Min-Cut theorem and say when can this AB not have a perfect matching?
When there is will be a cut such that the flow will be less than the total number of edges from S to A.
When the max flow is less than mod A.
Yes, so both of you are correct. So max flow is less than mod A, which means that min cut, because max flow equal to min cut, so min cut must be less than mod A, right?
Yes, sir.
Okay, so graph AB does not have a perfect matching. This implies that max flow is strictly less than n, not n, so mod A, right? Which implies that what? Min cut must be less than A, strictly less than A, which means that there exists a cut of size less than A, right? So let's say, I mean, cut meaning everywhere we are talking about ST cut, right? So let's say there is a ST cut. How will the ST cut look like? And maybe I can use a different color here. 60. An ST cut will have S in one side, T on the other side, and will cut somewhat. It will be something like this. Some of the vertices here would be in the S part of it. Some of the vertices here will be in the T part of it. Right. And the size of the cut must be less than N or A, size of A. Okay. And these edges, any edge that goes from say this one to here has capacity infinity. So if an edge crosses from the S part to T part, then it is of capacity infinity. So that will make the cut size of size N become much more than N. That is not possible. So I have a cut, ST cut, such that there is no edge from this S side to T side. Okay, at least in this graph. And but the total cut is of size less than N. Now think about it. Now work it out. From this, you will be with a little bit more patience, you will be able to prove that this can only happen when you find an A such that neighborhood of find a U in A such that the neighborhood of U is strictly less than U. Okay, is this high level picture fine?
The picture is fine, but
further say if the number of nodes in A and B are equal,
yes,
then mod U should exactly be equal to neighborhood of U.
That's mod A should be exactly equal to neighborhood of U.
Mod neighborhood of U.
If A and B are equal,
size of A and size of B are equal.
then mod neighborhood of A equals to neighborhood of B.
No, if I say both A and B have n people,
right?
Right. Then I'm saying that for any U subset of A,
right,
mod of U should be exactly equal to mod of neighborhood of U.
No, equal to. No, why?
Because so.
Then I mean, that can be bigger, right? I mean, see, this is a kind of this is a if and only thing that this is thing going on, right?
So I'm partitioning A into two sets, say A1 and A2.
Right.
And I'm partitioning B into two sets, B1 and B2.
Hmm.
Now I know size of A1 is less than equal to size of A2. Sorry, size
A1,
of
A2, B1, B2. And where is the cut? You don't have a cut.
No, the cut is like based on these partitions only.
Okay, so you mean cut are like this, right?
Yeah.
Okay, fine.
So A1, size of A1, I know neighborhood of A1 is equal to B1 and neighborhood of A2 is equal to B2 because there are no cross edges.
No, there is cross edges. There is cross edges. Be careful. Be a bit more here. There are edges from here to here. That is not going from the S side of the cut to the T side of the cut. These are going from the T side of the cut to S side of the cut.
Yes, got it.
Okay, there is no edges of this kind, opposite kind. This kind of things are not there. This is not possible.
Okay, sir.
Somebody else was saying something.
Sir, can you repeat this thing again?
Which thing? Just like this is what he told, okay? That's what your friend told, okay? So this is the cut, okay? And what I am guaranteed you is that the cut size is strictly less than n. Let's try to understand this cut size. What are the edges that it is cutting? First of all, the edges that it is cutting is C, right? It is this set of edges. It's coming, going from S side to T side.
Yes.
And it's this set of edges that they are cutting. Right?
Yes, sir.
So first of all, that means the cut size, let's say upper bounded, it is the size of A2 plus size of B1 plus, are the edges from here to here? Are the edges from here to here?
No, sir.
This edge is infinity. If there is even one edge from here to here, the cost of this cut would have become infinity. That would have violated my assumption that the cut size is less than A. Right? So there is no such cut here, no such edge like this. Can there be edges like this? Of course there will be edges like this. But they don't contribute to the cut. An ST cut, only the edges that goes from the S side of the cut to the T side of the cut contribute. Okay? So in fact, that means either there exists a cut from A1 to B1, in which case the cut is size way bigger than n, is infinity. Or if it is this, then the cut size is exactly equal to, if the cut size is, if the cut size is less than equal to n, then cut size must be A2 plus B1. And that means A2 plus B1 is less than n. Strictly less than n. Okay, I'm not saying anything more. You go and think this. Rest of it. Okay. From this thing, all you have to do is that from this kind of calculations and all, you have to produce a U and U subset of A such that the neighborhood of U is strictly less than size of U. If you produce this, then what do I know? Oh, see this, I started with a graph that doesn't have a perfect matching. That means then there must not be a flow. That means that the mean cut is small. That means I take such a mean cut whose size is less than A, and through that I can produce this thing. Right? This is exactly the opposite. I mean, the inverse, this side of the False theorem, right? That if a graph doesn't have a perfect matching, then there exists a U such that neighborhood of U is strictly less than size of U. Okay, I did not prove this, prove it for yourself. Prove it. I'm almost proved it, okay? Maybe some of you can also really see it. So go and think about it, you will have it. Fine?
Yes, sir.
What about the rest? Is it clearer than earlier?
Sir, the
Yes,
edge
sir.
from A2 to B1, that also have infinite.
Yes, but where is it going? What is an ST card? What do you count in an ST card? ST card is set some of the capacities of the edges that goes from the S side to the T side, not from the T side to the S side. What is the S side thing? S sides are the ones which are on this side of it. So this is S side.
Sir, understood, sir. Okay, sir. Got it.
Okay. Okay, good. So, nice. So now you guys are at least understand how to get Max-Krominkar theorem from Max-Krominkar. So note that I have not used any non-trivial algorithm. Okay, all I have used is this non-trivial algorithm, which is the Max-Krominkar theorem. That's it. That's a big theorem. I completely agree. That's a big hammer. But that's all that I needed. Okay. Okay, so now let me go a bit to a slightly different, although it's not very different concept. And this is something very magical if you have not seen this one. Sorry? Somebody said something? Okay, so if you remember, what was this network kind of stuff? The network, right? I basically wanted to sum up, I'm just writing it up, okay? I wanted to maximize the network flow, means maximize f of s comma u, sum over u, such that the flows have to have some properties, right? Which is it? For all e, f of e is less than or equal to c of e, and for all v or all w, sum of f of uw is equal to sum of f of w u, right? And I also had to ensure that these are for all e, these are all positive. So I had basically, so are you with me here? That in a graph, this is all that we had to do. This is what is definition of max flow.
Yes, sir.
Yes, sir.
Perfect. So see, what did I do here? All I did was that I maximized. So here, what are the variables? What are the unknowns? The unknowns are of course the f, right? All the f's are unknowns, right? C is unknowns, they are given to us, so no question. And we want to maximize a sum of unknowns, or rather this I can generalize it to say that I maximize a linear combination of variables, right? Under the condition that the rest of it, maybe I can use a green color. So this set are the constraints, right? And what are the constraints? The constraints are also not arbitrary. They're also linear, right? So I maximize the linear constraint when I am under the condition that the some linear properties are holds. Have you guys seen any of this ever before? Such a thing in some course? Numerical analysis or something? Hello?
12th class.
No. Whoever not in IS, I mean, I don't think it's the standard 12 plus thing, but other than 12 plus, I mean, in ISI, you have not seen any of that, right? Okay, fine. But you understand, this is very simple, right? So why am I getting stuck with this graphs and crap like that, right? Why not I generalize it to a general, so this is a general, it's called linear programming. Now you are all familiar with linear algebra, right? So if I ask you to generalize it to a basic concept, how will you do it? Oh, this is the top one is nothing but a linear combination of variables. Excellent. How do I do it? I maximize some C transpose X, where X is a vector of variables, right? And C is also a vector of known things. So X is a vector of variables. Such that the constraints, what are the constraints? Oh, of course, it's a linear combination of x's. How do I write linear combination of x's? Any idea? Okay. So you can think of this one to be a column vector, just to make it a bit more, if you are a bit confused. Let's say X is a column vector, so C transpose X is a linear combination of that. And this is A dot X is less than B. What is A? A is a matrix. And what is B? B is a vector. Is a vector of numbers, right? It's a known, all of them. So A and B are known. So what all things are not known? Let me write it down. X is not known, and X is the only thing that's known. Okay. So this is basically, you can think of it, it is this set of it. And sometimes people write it as, so I also want to make X to be greater than or equal to 0. Okay, let's say. This is. So this is general form of linear programming. You have a column vector of x's of random variables. You have A dot X is less than B. That's the constraint. And you have C transpose X, but X is bigger than 0. Right? Are you all fine with this?
Yes, sir.
So the inequalities are component wise.
Right, inequality is component wise. So A dot X is a vector, is a column vector.
Yes, sir.
Right? I mean, if A is a, so maybe if An is you write N, right? The N cross 1, right? C is also N cross 1. N cross 1 is a row vector or column vector? I forget this thing.
Column vector.
N cross 1 is a column vector, right? So good. So this is the N cross 1. And A is what? A is a M cross N. So B must be a M cross 1. Right, and similarly, yeah, they're all coordinates. Okay. Now, I will tell you that so you have done this thing earlier, okay? And do you know when I have done this thing? You have done it in class 8. Have you done things like 3x plus 4y plus 2z equal to 0 and say 2x plus 9y plus 9y equals to 3 and say x plus y plus z equals to 1. 10. Is there a solution? You remember this?
Only 2 variables till 10th class.
Don't tell me that. You are telling one side that you are doing in linear algebra in class 12 and you are doing 2 variables in 10th class?
Yes, sir. Most of the general things started in 11th and 12th. Like
Linear algebra we did in plus 2, 11th and 12th.
This is not linear algebra. This is just simple.
Yeah, simultaneous equations we used to do in 2 variables in the 10th grade.
Oh God. I mean, I'm so much out of touch with reality now. But whatever, you understand what I mean, right? I mean, okay, you know, I mean, yeah, I mean, oh. I mean, in class 8, I used to do, I mean, we had any number of variables of things. I mean, there was no inequality, but there was equality. Simultaneous equation solving was there. Okay, whatever. Sorry. So you have not done it in class.
Sir, in class 8.
Yeah, this is when you learn the basics of algebra. When is the first time you learned polynomial or algebra? X, Y, and so on? When do you learn quadratic equations?
So the quadratic equations in class 8, but the
This is
solving.
linear. This is linear. This is even bigger than quadratic.
Three variables.
Okay, whatever. I'm not going into this thing. But it
So
was.
I think the problem was mainly we used to do all of these things by graphing, right?
Graphing? No, you didn't do it by kind of cancelling it? Cancelling variables?
We did cancelling variables as well. As an introduction, all of these things were done as intersections of 2 lines, right? for 2 variable linear equations. So that's 8th, 9th, 10th was just 2 variables. From 11th, we learned like 3D and matrices and vectors, and from then we started multiple variables. And actually, even in 11th, 12th, there were only maximum to maximum 4 variables because no calculators and all.
Okay, I'm not sure whether education has gone backward or forward. Whatever, you understand that these things you could have done, right? I'm not talking rocket science. Literally talking about how to solve 3 variables with 3 equations, right? But whatever, whatever you have done doesn't matter, okay? But once you have it, now if I just make this one slightly different, okay? This is something we have not done for certain, okay? Is that I don't want you to have equality, but I want some inequality, okay? Fine, now you can ask whether it's solvable or not, right? But more importantly, I can even ask a little bit more. Can I say that maximize, say, 7x, sorry, plus 19y plus 5z, something like that. Now, if I give you this such a thing, right? You have a set of equations in 3 variables. So if I give you 3 equations, I also am saying x, y, z are all positive. Can you maximize this quantity? Okay. Now I'm not asking you to solve that question. But let me ask you a different thing. Can you give an upper bound of this maximization? Like, can this maximization, can this quantity, can the maximum be more than, say, more than 20? Or can it be more than, let me say, 50? Can it be more than 50?
No, sir.
No, why not?
Because x plus y plus z is less than equal to 1. And if we take 19x plus 19y plus 19z, then it will be less than equal to 19.
Oh, excellent. Very good. So you're saying that, oh, see, there is this particular equation here. Now, since it says x plus y plus z is less than 1, so 19x plus 19y plus 19z must be less than 19. And what I am asking you is 7x plus 19y plus 5z. So I am removing from 19x plus 19y plus 19z some 12x plus something like 14z. But 12, since x is positive, z is positive, so I'm taking away some positive quantity out. So I have 19 and I'm taking away something out. So I cannot get more than 19 for certain. Right? Good. Something else?
Sir, the first equation is implied by the 3rd and 4th equations. I mean the constraints in equations.
Okay, fine, maybe.
11, less than 11.
Why less than 11?
We can add we can twice the second equation and add it to the 5 times of the third equation.
Twice the second equation and 5 times third equation. Okay, excellent. So see what you are doing. Let me see. I mean, I'm hoping that you have doing it right. You are saying, okay, let's take the second equation and multiply it twice, and 5 times the third, right?
Yes, sir.
Now this will become 4x plus 5. So this will become therefore 4x plus 5.
9x plus 23y.
23y
plus 5z.
Oh, excellent. Is less than equal to 2 times 3 is 6, 11. So this is the case, and this quantity, okay, again we are getting this quantity by removing some constant fraction, well, some positive things out of this quantity, right? So this must be less than 11, right?
Yes, sir.
So in general, can you say something more in abstractly? You guys are all now students of ISI, right? You should be able to do something slightly more abstractly. What if I do say alpha, beta, gamma? I will multiply the first equation by alpha, second equation by beta, third equation by gamma, such that what? Okay, so if there exists alpha, beta, gamma, such that, meaning 3 alpha plus 2 beta plus gamma is more than 7, right? Similarly, if you look at this thing, 4 alpha plus 9 beta plus gamma is more than 19, okay, plus 5 alpha plus, not 5 alpha, 2 alpha plus 0 plus gamma is more than 5. If this happens, then I know that the quantity, then the optimum must be less than optimum, meaning optimum of this thing, this is called the LP, maximum of this LP, must be less than what? 10 alpha plus 3 beta plus gamma. Is it clear?
Yes, sir.
I couldn't follow. Means what is the alpha, beta, gamma here?
So you are weren't you the person who gave me the idea about multiplying the second equation by 5 and 2 and
Yes, sir.
now why not just you have multiplied the second equation by 2 and third equation by 5, right? And then you can multiply the first equation by alpha, second equation by beta, fourth equation by gamma. Okay?
Okay.
Who cares?
Oh, we are equating the coefficient. No.
Yeah, and just I'm saying that just look at the coordinate of the coefficient of x. That coefficient of x must be less than this 7. Coefficient of y must be less than this 19. And coefficient of z must be equal than this 5. Right?
Yes, sir.
And then the constant term that you have, that will be an upper bound of the optimum.
Yes.
Okay. So this basically, if you try it out, right? So this is exactly like you are trying to find whether there exists such a thing, and your goal is that, oh, can I come up with the best alpha, beta, and gamma? So this quantity is minimized, right? The minimum this quantity is, the better the bound on the optimum that we will get, right? So I can ask the same question as like, oh, okay, fine. Therefore, you minimize this quantity, minimize this quantity such that this holds. Do you see? So if I call this one as what is called as a primal, so primal is maximize something under restricted to something. I have managed to produce something else which is called a dual. Okay? And it is minimize something that is restricted to this quantity. And you can see that primal, meaning the best solution of primal, must be less than the best solution of dual. Right?
Yes, sir.
Right?
Yes.
In fact, there is an even bigger theorem which says that this was equal.
So we can take the dual of dual, right?
Dual and dual will get the primal.
Sorry?
Dual and dual will give you the primal value.
Yeah. So this equality is trivial.
No, of course not.
But dual of dual is primal. We already know primal is less than dual.
Yeah, but okay, so good. So here the primal is because it is the max. If I have written primal in terms of the mean, then the dual would have been the max. In this case, it would have got the opposite direction.
So dual of the dual will be the prime, exactly the primal, will be max.
But dual, so let me, if not, if you, maybe this is confusing. So don't call it primal, okay? So I will call it the max. Okay? Why max? Because of this max. And this is mean. Dual is, I can call it mean. Okay? So what I have is that max is less than equal to mean. Now, if you have take mean and take a max out of it, you will not have mean is less than max. You will again have max is less than mean.
Okay, so if our initial problem was about minimization,
right,
then this thing is kind of useless.
That will be the opposite direction. Right. If the original problem, primal, is a minimization problem, okay, then the dual will be a maximization problem, and then you will have the minimization problem is more than the maximization problem.
So we can take the negative.
I mean, you can always think of that max is less than mean. No, by the way, equality is not a trivial one. Okay, this is one of the most celebrated theorems in whole of area. If you, I mean, you are in BStat, so you, if assuming that many of you will continue for MStat and all, you will see it. This is what is the starting point of operation research. This is the starting point of optimization. This is called the primal dual, primal duality theorem. Okay, it's not easy. Again, right? It's a pretty non-trivial statement. That primals and duals are there. One direction is easy to see. This is easy. The fact that it is exactly equal, it is not easy. But it is true. Okay? Just 1 second, I have to go and see something. Hello? Hello?
Yes, sir.
Yeah. Sorry, but okay, so good. So what did we start? We started with the Max-Flow-Minkert theorem, and we told that, oh, that is a special case of a primality, a maximization problem in the LP. And if you have an LP, there is an equal amount, then you can upper bound the LP or the max optimization problem with a duality, dual formulation, and the primal is equal to dual. Or in other words, max is less than equal to mean, and in fact, what you can prove is that this is equal. Okay, I have not proved it. Do you see any close connection to somewhere else? Started with max flow.
Max flow theorem.
Exactly. Max flow equals to mean cut is actually a special case of this thing. Primal equals to dual. Okay, I wrote the max flow in the primal world. If you now generate the dual of this with a little bit more, basically calculations and not calculations, but pushing around the variables correctly, you will get the mean cut. Okay. So this basically is a completely new area that comes out. I am not going to go into more further, but let me put it there. So what we have seen, just 1 second again. Hello.
Yes.
Yeah. So we have this linear programming, right? Now there are certain things that I am going to say, which I am not going to prove now. First of all, it's a big area of research. And what did we see of the linear programming? Let me quickly write it down once. Okay. So we wanted to write it as math. So I'm writing in terms of the maximization problem only. You can write it in the terms of minimization problem also. Maximize C transpose X such that A dot X is less than or equal to B and X is bigger than 0. Now, one thing that I have not written here, but it was kind of obvious, that X is in the reals. Okay, X can take any value.
R power n.
Yeah, R power n. I mean, meant R meaning the sexual third R, but yeah, R power n. Okay, fine. Sometimes people, just to make it a bit more bounded and all, it is written as 0, 1 to the power n. Again, it doesn't matter so much. We scale it up and down and everything works. Okay, this is not a big deal. Now, first statement is one thing that I proved, that for every primal there exists a dual such that the primal equals to dual. Okay, this is a theorem. I have not proved it. I have just given you a hint of it. Second thing is that this another big theorem. I'm not proving it. Maybe if you have a second course in algorithms, you might be doing it. Okay, that LP, this is called LP. This can be solved in polynomial time. I don't know whether you have heard of it or not, but this was one of the big results in the 60s with a collection of results. And it's still a major area with the ellipsoid algorithm. Before ellipsoid algorithm, there's something called a simplex algorithm. Then there is there's an Indian guy called Karmarkar. He came up with an algorithm. It's called the integer point method. There's a collection of work, and even now it's a massive area in mathematics. Coming up with the efficient algorithm to solving LP. We now know that this is there. You can do it in polynomial time, but this power, why people are so excited about this? It is exactly the same reason why people are so excited about graphs, or why people are so excited about flows, because many problems in the world can be modeled in this form. This is a very general form. Very general form. Okay, many theorems can be general form. Now there is slightly more versions, there are slightly more generalized versions of this. Okay, and this is what our focus of our main thing is. There exists generalized version. Now, one generalized version that is very useful for our setting is that instead of having this x to be 0, 1 to the n, you make x to be integers. Okay, either rev to the n, or you can think of it as Boolean 0 to the n. Okay. Now we go from reals to discrete, and there things are very hard. So I told you in the beginning that there are many things that you have to do it in by Tuesday or something. So one thing that I will do is that we will give you a collection of problems. Okay, they're all easy problems. Many of them you have seen. Okay, for example, what is the maximum matching that you can have, or what is the maximum match test problem, or maximum length of the the common subsequence, or least common subsequence, or many of these questions that we have seen till now. All of them can be written in this form, not with the R, but with this. These are called the ILP, or integer linear programming. Now, the integer linear programming has a big problem and a big advantage. The advantage is that, first of all, almost any problem that you can think of, or you can think of, there are a lot of problems that are not in that, but many problems that will come to your mind can be written in this form. So this is a very general stuff. Okay? And this is what I want to prove to you guys by your example track. Okay? Pick a problem and write it in the ILP form. Okay. Chandrima, are you there?
Yes, sir.
Can you just note it down? We have to post a set of problems today.
Okay.
Okay. So basically, I will say most problem. Now I will define the most very soon. Can be written as an ILP problem. Okay. Some of them can be written as an LP problem also. Okay, but some of them can be written as an ILP problem and not as an LP problem, not that we know of, right? And the second and the disadvantage of ILP is that there does not exist a polytime algorithm. So once we kind of convince ourselves that there is an ILP problem that is a big problem, so what we will have this, we will call this algorithm as a complete problem. Meaning almost every problem can be written into ILP problem. I will mathematically formally define what a complete problem is. Next week. Okay, we can define a complete problem. So here is the problem that is the hardest problem in a class among a class of problems. And the problem is that we don't know how to solve it. Okay. And this is what will be the main focus of ours in the next week. Okay, we will be going more towards the area of slightly called complexity theory, where we will be delving with such a things. Now, there are other generalizations that can also be asked. Okay, for example, why just linear? Why can't we do something else? And there are things, okay? I'm not saying there are not things, there are things like the convex optimization. There are things like what we call as semi-definite programming. So you can think of semi-definite programming in the special case of quadratic optimization, or it's called SDP. And it goes on and on for something which produces a completely new genre of work. It's called Lasserre hierarchy. I mean, these are all beyond the scope of this course. I'm just giving you these names just in case you are interested in. And possibly complex optimization, I know is a part of your MStat courses. SDP also you will be seeing a little bit of it out of the MStat courses. Cluster hierarchy, I don't think you will see. Yeah?
We have a class from 1.
Yes, so I'll stop. So basically what we have is now, we have this LP, we have the ILP, and we will be posting you a collection of problems that you will have to think and write it in form of an ILP. Okay, and once you are done with that, we will take it from Tuesday onwards accordingly.
Sir, primal equal to dual may not hold in ILP.
No, it is not true in ILP. Not in general. Not in general. Yeah. Okay, good. So let's stop. I mean, we'll meet again on Tuesday. Okay. See you.
Sir, what is the sixth thing?
Sixth thing, Lasser hierarchy. It's like the higher, I mean, instead of you have linear, then you have quadratic, semi-definite program, you can call it quadratic, and then it goes off to higher degrees in some sense. Okay. By the way, you can view all of it. If people are more interested in geometry, you can view all of this thing that we have talked about in the geometric world. Because what this thing is kind of defining, okay, this polynomial, by the way, if whoever wants to look at this, okay, so you have to define this kind of stuff. This gives you a polytope in a n-dimensional space. And this is a vector, right? You have a polytope and you have a vector and you're trying to understand what is the maximum thing that the vector can do. So basically, that's what we are talking about. Okay. So yeah, maybe we can talk about it later. Maybe not related to, because that is not related to the algorithms or complexity part of it as such. It is more from the point of view of optimization part, which we will take up later on, in a later course. Okay, let me stop here. We'll meet on Tuesday. Good.
Thank you, sir.